Alright, so I just wanted to mention a little bit of an example here. It's in the notes, but suppose I've got a few data points here. I've got a data point here, I'm going to label it as A. Data point here, I'm going to label as A, so that's class A. Then a data point way over here, I'm going to classify as B. And then I'm going to say, here's an unknown point. What should the class label be? Well, it looks like the class label should reasonably be A. Right? However, what happens if I say that down here, this is 0.1, 0.11, and this is 0.2, this is 1000, this is 1500, this is 2000. Well, if you were to use the nearest neighbor classifier, what you would find is that the distance from our unknown point to each of these other points, the distance from here to here and the distance from here to here is actually going to be 250,000, but the distance from here to here turns out to be 0.008. Okay, so you see what's happening here. If we use Euclidean distance, it's very important to make sure that the variables are scaled appropriately. Scale the variables appropriately. Right, because what ends up happening is that you're just measuring the y. In this case, you're not measuring the x-axis at all because the scaling is so bad. You're just on the scale of 1/10 on this side, but you're on the scale of thousands on this side, and so the algorithm is just going to focus on the distance in the y-axis and just completely ignore your x-axis altogether. Okay, and so do you remember how we do that? I think we've rescaled the data a couple times before. There's a couple ways to do it. So rescaling, the one I like to use is to take your x and then replace it by x minus x bar divided by standard deviation. So this makes sure that your data has zero mean and unit standard deviation. Okay, so the spreads are somehow equivalent. Another possibility, though, is to take x and then scale it so that scale so all data is in the interval from 0 to 1. So how would we do that? Let's see, x minus the min of the data divided by max minus min. So notice what I'm doing here. So if x was actually the minimum value of my data, then I'd have 0 in my numerator, and so the minimum value would map to 0. And then if x is equal to the max, right, I'd be dividing by 1. And so the max would map to 1. And so all the other data would map in between. Okay, so that puts all your data between 0 and 1. So this is, I think Python calls this the standard scalar. Darn it, my hand is moving something. Darn it. The standard scalar. You can look up the other one. I don't use it very often, so I don't know what it is. MATLAB also has these built in. It used to be belong to the old neural network toolbox, but They've been messing with that. I don't think it's available anymore, so we'll have to just do it ourselves, I guess. All right, so rescaling is really important when you're working with the Euclidean distance. Of course, I should say that you don't have to rescale your data. You could change the metric instead. Right, so this is actually rescaling it, but you could, instead of taking your metric to be delta x squared plus delta y squared for your Euclidean distance, I got stuff flying around here on my desk, you could change that so that you're scaling by some alpha 1 here and an alpha 2 here. But this is probably harder to do. I would recommend scaling the data rather than changing your metric. Rather than changing the metric itself, because that's harder to remember. Scaling the data is easier to remember. Good. All right. So what we've talked about so far is just the nearest neighbor algorithm. How would we change this to the k nearest neighbor classifier? Well, the idea doesn't change by much. If this is your data with labels and this is your new point, then you find the k nearest points to that. In this case, let's take 3. And so then you look at the labels, and these may have different labels, right? So this may have labels like A, and B. And so the way you would label your new point, what would you guess? Did you guess the majority rule here? That's typically what you would do. So you would see which class label is appearing most often, and then you would use that as the class label. Okay. Okay, so there's another way to do this. I'm kind of thinking about these labels here, and in the majority rule case, I can think of doing a count, right, for each class. And so I could say class A has a count of 1 plus 1, which is 2, and class B has just a count of 1. And so then you just choose the class with the highest count. The way we can generalize this is that instead of just looking at the labels themselves, you would track the distance for each of your points. So I would write down d1 for the distance for this first point, d2 for the next, d3, and so on. And then in class A, right, if class A is the first 2 points, I would say that this is 1 over d1 plus 1 over d2. And then for class B, it would be 1 over d3. And whichever is bigger would be the class label. Biggest is class label. And so, do you see why we would do that? If a data point is really close to your point, then that would mean that this number, this score, if you will, would be very large. And then if the distance was far away, then the score would be very small. And so what this does is it gives much more weight to local points than it does to points that are far away. And so that's kind of a nice way of doing those as well. We'll compare those later. All right. So I just wanted to mention a couple of extreme cases since we're talking about the k nearest neighbors. What happens if k is equal to 1? Well, if k is equal to 1, of course we're back to the nearest neighbor situation. But you'll notice that if you use training data to test the classifier, we get 100% accuracy. And that's because all we're doing is memorizing the data at that point. What's another extreme case? Another extreme case would be if k is large enough that you would take all the data no matter what point you use, right? So notice that in this case, if we're not using a weighted average, right? If we were just doing majority rule, this would always be the same class. Always would predict the same class. That's the one that has the most labels. The one with the most labels. And so you wouldn't want to use these extreme cases typically unless you had a really good reason to. So what does happen in your data set, when you have different classes? So if I have like dots for one class, maybe x's for another class, right? What would happen is, when you're trying to find the separation between these two classes, you probably don't want to do something like this. Oops. Oops, I just lost my data point. Well, you get the idea. Here what I'm doing is I'm trying to carve out the space so that all my points are good, and so this would give me 100% classification. Rather, you'd probably want to try to find like some general dividing curve or dividing line in between. And so this actually is what happens when you increase the value of k. So for low values of k, low k means that the boundary is more complicated or more complex. As you increase k, the boundary smooths out. And so typically you want your boundary to be fairly smooth. This is what we mean by a generalization. We want a smooth boundary between the two classes, even though we're introducing some error, because it looks like that will be generalized to the new data better. So it generalizes to new data better in general. Generalizes to new data better in general. Okay, now I should say that some people have a rule of thumb for this, and so I'll just give you the rule of thumb. I don't really abide by that very much, but rules of thumb are a good place to start. K equals the square root of n, where n is the number of data points. And so if you have a small number of data points, right, your k would be small. And if you have a huge number of data points, your k would be large. Good. All right. So there's lots of questions that we have at this point, maybe. So for example, how do you find k? So we're going to get to that, but before we do, we need to talk a little bit about data in general and some ways of measuring error on data. So we'll get into that in the next video. If you're following along in the notes, I hope you are. That's page 120 in the next video. See you then.